The idea that you can put a production-grade artificial intelligence data center in your front yard is gaining serious traction online. It sounds like the ultimate solution to cloud costs and privacy concerns. But the reality of the physics involved suggests this is not just difficult, it is thermodynamically impossible for residential settings. By the end of this explanation, you will understand exactly why the math works on a spreadsheet but fails catastrophically in the real world. Let us start with the hardware comparisons that drive this hype. You will see articles suggesting that an NVIDIA Jetson Orin Nano or a Mac Mini can replace cloud subscriptions for a fraction of the cost. These sources cite a 3-year savings of $1,000 based on idealized inference tasks. This narrative relies on the assumption that running a small model is the same as running a large-scale training job. It is not. The difference lies in the heat. When you move from a single inference task to a sustained production workload, the energy requirements do not scale linearly. They scale exponentially. Consider the specific hardware often proposed for these so-called mini data centers. There are proposals for an XFRA node specification that packs 16 Blackwell RTX 6000 GPUs into a single residential rack. The marketing materials suggest this is a viable home setup. But let us look at the numbers. 16 of those high-end GPUs generate a thermal load exceeding 150 kilowatts. To put that in perspective, a typical American home consumes about 10 kilowatts of power in total, including heating and cooling. A single rack of this hardware would generate 15 times the total power usage of an entire house. This creates an immediate problem that no software architecture can solve. You cannot simply plug a rack of this size into a standard wall outlet. The electrical infrastructure required to support 150 kilowatts of continuous load would demand a dedicated 400-amp service upgrade. This is not a matter of flipping a switch or buying a better circuit breaker. The National Electrical Code does not permit residential circuits to handle this kind of instantaneous inrush current or continuous load. Installing a 400-amp service is an industrial project that costs tens of thousands of dollars and requires permits that most homeowners cannot obtain. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Even if you could solve the electrical supply, the heat dissipation problem becomes the showstopper. Industrial data centers use liquid cooling systems that circulate coolant directly through the chips to remove heat at rates that air cooling cannot match. A front yard enclosure, however, is a passive or air-cooled environment. It lacks the pumps, the radiators, and the chillers required to move that heat away. When you pack 16 Blackwell GPUs into a rack without liquid cooling infrastructure, the temperature inside the enclosure rises faster than the air can carry it away. The result is immediate thermal throttling. The processors detect the excessive heat and automatically reduce their clock speeds to prevent melting. This means the theoretical performance metrics, the tera operations per second that the marketing materials tout, become completely unachievable. The hardware becomes a brick that is too hot to touch, not a supercomputer. The physics of thermodynamics dictates that you cannot contain that much energy density in a small, uninsulated space without active liquid cooling. This leads us to the economic argument that often accompanies these proposals. There is a model suggesting that you can get paid to host this infrastructure and lease out your compute power. The math suggests that the revenue from compute leasing will offset the costs. However, this calculation ignores the operational expenses of enterprise-grade cooling and power redundancy. In a professional data center, you need N+1 or 2N redundancy. This means you have duplicate power supplies and cooling systems so that if one fails, the other takes over instantly. In a residential setting, you do not have this redundancy. If your cooling system fails, which is highly likely given the thermal load, your hardware will fail. The cost of maintaining 150 kilowatts of heat dissipation in a non-climate-controlled outdoor environment would likely exceed any revenue from compute leasing. You would be spending more on cooling infrastructure than you could ever earn back. The pay-you-to-host-it model fails because it assumes a stable power grid and active cooling infrastructure that residential settings simply do not have. Furthermore, the software architecture behind these blueprints relies on distributed storage stacks like AI Store. These systems are designed for edge nodes that have stable network bandwidth and low latency. Residential internet connections are rarely stable enough for synchronous multi-agent training. The network becomes a single point of failure. If your connection drops, the entire cluster stops functioning. This turns your mini data center into an isolated compute island rather than a scalable cluster. The complexity of vector databases and multi-agent orchestration implies significant background resource consumption that contradicts the low-power narrative presented in the hardware comparisons. We are left with a fundamental disconnect between the theoretical software architecture and the physical reality of residential infrastructure. The software can be deployed anywhere because it is just code, but the hardware that runs that code has physical limits. The argument for miniaturized residential data centers remains theoretically sound in the world of blueprints and GitHub repositories. But in the physical world, where heat must go somewhere and electricity has limits, the concept collapses. The exponential rise in cooling requirements as compute density increases creates a barrier that no amount of software optimization can overcome. The insight that changes everything is this: the thermodynamic reality of packing high-end GPUs into a rack-sized enclosure without liquid cooling infrastructure results in immediate thermal throttling. The theoretical performance is unachievable in a passive or air-cooled residential setting. You cannot cheat the laws of physics. If you try to run a 150 kilowatt load in a house, you will not get a supercomputer. You will get a fire hazard. The edge AI hype ignores the fact that energy density has a hard ceiling in residential environments. Until we develop residential-grade liquid cooling that is safe and affordable, the front yard data center will remain a fantasy. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.